Hello and welcome to this fantastic Pitch 200 event. My name is Ryan Clarke, and I'm here today to talk about tensegrity structures. So I'm a graduate of 5 months working with AECOM in its water division. Today I want to talk about something that's not actually connected with water, but I want to explain this engineering topic because I think it celebrates what the ICE has done over the past 200 years, but it also looks at the future of the ICE, and it also creates a polarizing look at how we look at design and buildings. This isn't your traditional bricks and mortar approach, but it's a cabling and bar system. So that's tensegrity. So the name tensegrity, it was first patented in 1962 by an American professor called Buckminster Fuller. So tensegrity, as you can see there, it's tension and integrity. So you can see here from my prop that the bars are in compression, whereas the cables are in tension. So it's the tension that keeps the structure together. So initially then that was only used in the likes of architectural art installations and sculptures. So that's like the ones we see here, and even my one. However, whenever you look into tensegrity more and look at the design loads in it, if you apply a load somewhere in the structure, it gets impacted somewhere else. So if I squeeze it here, you can actually feel the load in the back strings. So what that means then is tensegrity can be used as an efficient way of design. It's new and it's modern, and it's becoming more mainstream due to the way it dissipates forces throughout it. So some examples here we have then shelters and pavilions. Then we have building facades, and this is a football stadium roof in Argentina. This is the Clarke Bridge in Brisbane. Tensegrity has the ability to be a everyday sustainable solution to design issues because it is efficient in the way it dissipates loads. It's then able to be material efficient as well. And here you can see it's used in transport. It can be used socially in buildings. It's environmentally efficient due to product selection. So here then is another example. This is AECOM's Beacon Pavilion in California. This is the most recent event that I could find on tensegrity. It was used for the Coachella Music Festival. So over 100,000 people were in this tensegrity tent over the past, over a space of 2 weeks. So it's been, it's material efficient and it's sustainable, but that's the past and the present of tensegrity. I want to talk about the future of tensegrity. That's what makes it so exciting. Tensegrity is currently being developed because it can be deployable, so it can actually be flat packed. I don't want to do it on my prop in case it goes, but it can be flat packed and then deployed. So that's currently used in the likes of disaster relief and after natural disasters to make pop-up shelters. As well as that then, one of the biggest advancers of tensegrity is NASA. They're currently developing, here you can see on the left, their super ball bot, which if you look at it, it's, it's the same as mine. I made mine in my kitchen last night, and that's one made by NASA. That's that's a planetary explorer, so they're going to flat pack it and launch it at Mars, and then it'll be able to deploy and actually move on the surface. So what tensegrity means is that we can have efficient buildings that are aesthetically and architecturally pleasing, but they also have a real purpose. And so this is another example here, which is an antenna which currently maps the Earth, and it was a tensegrity flat pack design. So that's me. Thank you for listening, and if you've got any questions.
Ryan Clarke, ladies and gentlemen, let's hear it for him. Start this time with the time, if that's okay.
The time was 240 seconds.
Tense. And now from the judges.
Good stuff, Ryan. That was really interesting. I'd like to know, are there any downsides to this? You didn't touch on that.
Well, one of the downsides would be, what if I took one of these cables out? It wouldn't be long falling apart. But again, that's because I think it's actually going to go here if I set it down. But that's a prime example. But as you build larger and there's more cables, it gets more it gets more integrity from the cables. So that's one downside, but it can also be countered.
Can I ask a quick question about
Yeah.
football? Can you
Yeah.
put it back to the football stadium?
Yeah.
For all of us who are missing Manchester United in the Champions League tonight, it's a good chance to talk about football. What's the benefit of this sort of technology in a football stadium? What can it do that Windsor Park doesn't have?
Well, I think the main advantage is maybe Windsor doesn't look like that. It is, architecturally and aesthetically, good to look at. But I'm not sure about that particular example. But because it is deployable, you could have then an open and enclosing roof, and it would be, completely untraditional, which is sort of what I wanted to show here.
Thank you.
Ryan, thanks very much. I hadn't a clue what you were going to tell us about tonight, and I didn't even Google it, and I thought I'll just go and be a newbie in the audience. So I'm obviously delighted and really interested in what you've done. Two things. One, cost, and how do you make sure it doesn't blow away?
Well, the blow away question, there isn't strict rules over tensegrity, so you can have a strict tensegrity system, which is one like this, where it stands by itself. But then you can have unstrict tensegrity systems, the likes of the bridge you can see there. It has other supports because it's more practical.
I think you're cheating.
Well, it's still different, it's still. And what was the other question, sorry?
No, that was cost then.
Oh, the cost?
Cost.
Well, the cost then is, the big cost would be in the fibres, where you got to get the material selection so that if you cut one, then it won't fall apart. But the main thing with cost is it can actually be cost efficient because of the way it spreads loads throughout it. It can actually then be an efficient way of design because you can design it to have less members because it's getting dissipated through the whole structure.
Okay, well, it looks superb, so great. Well done.
Any questions from the audience? Make yourself known.
I can't see. Anyone? All right.
So just maybe to follow on from the question on the disadvantages, are there any disadvantages around decommissioning of tensegrity structures?
Well, the main
Or advantages?
The main one would obviously be health and safety. If I ping this wire, that whole thing could go flying, So that would be your main worry point there, the health and safety in terms of it is tensionally, the whole thing is pulling together. So there's a release of energy then if you try and decommission it. But again, it just depends on the individual project, I guess.
Anybody? Oh, at the front here. Do I just take mine?
How you doing? Would you consider it as a possibility to deploy at the end of a drill hole to use as a ground anchor for certain very fissile or sandy soils?
I'm not sure, but again, I'm sure that would be possible because it's very diverse, and again, it is quite modern. It was only patented in '62. That was the name of it. So again, it's very diverse. So I'm sure that it could be developed for something like that. Yeah, absolutely.
Hi, so for like normal structures, we have a factor of safety. So in terms of the health and safety, does that mean then we have to over-design for the factor of safety in this? If you say if one of those cables break, does that mean then that you have to over-design for the factor of safety?
Well, I think part of that would maybe be if it is a huge structure that the tension in each load or in each cable is lower. So maybe it depends. It depends on the project. Obviously, you have to design with a health factor of safety that will be involved in any project, really. So I knew that was going to happen. I told you it could flat pack. So there's the proof. Cheers. Yeah, there you go.
Any more questions from the audience, people? Okay, give it up for Ryan Clarke one more time. Excellent stuff.